Yeah. It's fun. The thing about the new Spelunky is I'm still set in my muscle memory from the first game, and this one you can take your time and go a lot slower, and this one I just want to rush to the end, and I inevitably make mistakes because I'm rushing things. But that's just how it goes. Good morning. All right. Oh, before we get this going, um, announcements. So up on Blackboard under term project and in whichever order Blackboard feels like ordering it, it seems, I added the final presentation information. So this will be ideally like a continuation of your midterm. The camera is slightly rotated, I'm just noticing. Okay. Again, I kind of want to try and celebrate all your hard work and see all the really neat things everybody's done. So don't take it as something to formally stress out about, but just kind of looking for information about your project. So just for formality's sake, introductions, what your project is, just so that everybody remembers. Um, and then things that have changed since the midterm. So did you actually hit all of your timing goals? Because again, you came up with Gantt charts or burn down or burn up charts. Did you make those? Did you not make them? Kind of a little reflection almost. Always be stressing. No worries. Happens at all levels too. So then from that point, what has changed since the midterm? So obviously we saw either an early look or a beta or something of what you were all working on. So where are you at now, basically? And then since testing was kind of the big addition here, what was kind of the focus of your testing strategy? So were you looking at particular components? Did you do something interesting for your test plan? Just kind of walk us through how you did testing, I guess. And last but not least, a demonstration of your project. I know you're all doing really cool things, so if other people are interested in your project, maybe a short discussion of how to get it up and running. And that's probably going to be a part of install Unity and download project and import or buy an Arduino and do this or something like that. But since everything is forcefully being open sourced for this class, anybody should be able to go and download what you're working on and try it out. So just kind of a little overview of how to run it for everybody else. But that's basically the final presentation. And in the announcement I sent out, I also added on a little addendum that I'm going to have you all do a very small writing assignment. So kind of a little self-reflection on the project, little evaluation of your teammates, things like that. It will be not very much effort from your part, but something that will be useful for me for grading, basically. So that will probably, I won't make it due next week Friday, so I have time to read through it, but it's only to be like a paragraph or so. Nothing to really worry about. But then that's going to be about it for class. So you just have three deliverables. So upload your presentation, upload your deliverables, do this to be defined reflection, and then that's pretty much it for me. Um, so this whole thing is due Friday, next week Friday, yes. Yes. Yeah, so that's the last day that I can um, get everything down so that you can get a grade from the school on time. You can turn everything in early too if you want. If you're going to be ready to turn it in on Monday, feel free to turn it in on Monday and then I will grade that and put it into Blackboard as early as I can. So then you have an idea of your final grade in the class. You are presenting on Monday. So let me pop that into chat here because Monday is the day of our final exam. So that's the time that everybody has for getting together, basically. It's the time listed in the syllabus. and in Blackboard. Yep. We have time to do all presentations. Yeah, so we have 2 hours for class. Um, we have 2 hours for class for the exam. We have 8 groups. So if we limit everybody to 15 minutes, that should be enough time. I'll probably be a little harsher with limiting everybody because it's not like you're missing class if it spills over, you're missing an exam, which is bad. So I'll have my little timer up and running and I'll cut you off and ship over to the next group. As long as you are hitting the requirements for what you need to talk about, um, and it's a reasonable presentation, you can be flexible there. And keep in mind, this is time for you to kind of toot your own horn and show the really nifty things that you worked on over the semester. So don't don't give yourself the short end of the stick with that. Be proud of what you did because everything that I've been seeing so far is really exciting. I can't wait to see the final deliverables. Even if it's half done or I mean minimum viable product done. I mean, if you still have like 2 years worth of polishing, at least you have a prototype, which is super cool. I think anyway, but I'm biased. I'm the professor here. All right, let's talk V and V in a little bit more detail. So everything that we've been talking about so far, we've been kind of nipping away at more and more detail as we go, right? We started very, very high level. Last time we started talking about V and V again, kind of at a high level, some best practices, what you should and shouldn't be doing. And today we're actually going to start talking about some actual testing techniques, right? Not just unit test, quote unquote, or integration test, quote unquote. We're actually going to talk about methods for testing. And we're not going to go, crazy. There are probably a zillion techniques out there. We're going to look at a few of them, some of the more common ones, and you can kind of explore more from there. In whichever environment you go end up working in, whether it's at a big company, whether it's a startup or your own personal business, you're probably going to have your own testing method. But what we'll be looking at are some of the more common ones. And these will really get you, kind of get you started. And if you can understand these, then you can pretty much understand any of them. It's, again, more or less common sense to me. You're just checking to make sure that your program works, right? So what are we going to be talking about today? So we're going to talk about testing techniques, and we are also going to talk about static verification and debugging techniques. So the first one is going to be mainly today. Next time will be more static verification and debugging. Um, those are going to be more so looking at your actual software artifacts, like your requirements and your models and so on and so forth. What we're going to be talking about today are actually performing the validation where you're checking input and output values or checking paths of execution. You're going to vary in complexity. Hopefully they're common sense. All absolutely necessary to make sure that your project is good and that you're going to make your deliverables. So, revisit to our favorite words of the class, black box and white box. I guess the other favorite words would be trade-offs because that's also software engineering. But here we have two of our different techniques, right? Black box and white box. I told you to get used to hearing it because I would say it multiple times. Black box, again, is where you're checking the input and the output values and you don't really care what's happening inside. You just want to make sure that your thing that you're testing is taking in the values you expect and outputting what you expect. You don't care what's happening inside. Right? You don't care if it's bubble sort versus radix sort versus Q sort. You just want sorted list at the end. White box is a little bit different, right? We know what's happening inside, which means we can test the logic of the program, the algorithm. We can make sure that all of the conditions that we're putting in there are valid and are being checked. So basically, there's a little bit more to it there. With black box, it's going to be pretty straightforward to talk about. We've got a couple of methods here that we'll be covering. So equivalence, partitioning, and boundary value analysis. These are two ways of basically being systematic about our testing strategy. I'll talk about that again in a few moments. White box, we're going to be looking at which paths of execution are being followed. You want to make sure that all of your code is properly checked. All right, so let's start with black box. Um, if you go into industry, you may also hear this called functional or behavioral testing. Basically, you're just making sure that object does thing correctly. And what does thing correctly mean? That's whatever you specified in your requirements or your models or your artifacts, whatever you're using to check as a ground truth that your project is doing what it should. We're again checking, does it do this based on this? So again, check the input or send inputs, check outputs. Basic black box testing. And the interesting thing about this is that when you do this testing, it's going to be dependent on your requirements and your test cases. Sorry, that is my kid's alarm. 1 second here. All right, sorry about that. Kitchen timers are very loud. Um, everybody's schooling from home. Alrighty, so where was I? Testing. I was giving you an amazing, wonderful example, I'm sure. Um, oh yeah, all right, that's right. So with testing, it's only as good as your requirements are. So it's very important that your requirements are checked and they're validated, and you make sure that your software requirement spec is valid, that your test cases you've written are valid, because you're testing to that. You don't have some magical golden rule that says, well, this test case passes, that means your program's perfect. No, it means that your program's doing what you said it should be doing. So you also have to make sure your requirements are in line, which we'll get to at the end when we talk about static validation or static verification. So with testing, and black box testing in particular, we're going to be mainly looking at this kind of towards the end of the cycle. So when you're getting to integration testing and beyond, basically you're more so looking to make sure, does your program do what it should be doing appropriately, right? Again, inputs versus outputs here. That's what your customer sees, that's what you are checking to make sure works. Now, are you doing all these other types of tests? Absolutely. But this is more to make sure that you're functionally doing what it should be doing. Think back to your requirement spec, you had functional requirements, right? You're testing those functions, is effectively what we're doing here. Now, what do we get out of this? Again, if we're checking at a black box level, we do not know the internals. So what are we finding test case wise? We could be finding, say, interface errors. Maybe there are modules which are trying to talk and they're not being invoked correctly. Maybe you're calling a function wrong. Maybe a function's missing, in which case you get a compiler error, or if you're in Python, you would find out after it starts running. But maybe you're sending in the wrong data. Maybe it's formatted incorrectly, right? You could be accepting a generic object and doing things with that object later on, only to find out your object is empty or it's in the wrong format. So this is kind of the stage where you would find issues like that. You could also find behavior performance issues. So if we are black box testing, could be looking at performance or usability. Maybe it runs really, really, really slowly when you get to the fifth screen deep in an Android application. And then you have to figure out why that is. Do you have too much in memory? Is it calling a cloud service a million times and waiting for a response? Did you do the cheeky thing and put a little bit of a delay in there to make it seem like it's going slow so that you can speed it up later on? But these are the kinds of errors you'd typically expect to find here. Next slide, please. When you hit right, it should go right. Okay, so equivalence partitioning is going to be the first thing we talk about here. And if you remember a couple classes ago, we talked about exhaustive testing, right? That's where you're checking every single value under the sun, every single combination, and we realize it's going to take years upon years upon years to hit that mark, right? Simply checking A plus B took, what, 600 years, I think the value was? So what equivalence partitioning is going to do is give you that systematic testing idea. You don't have to check every single possible value. You have to check representative values. Because when you're doing that kind of testing, you're kind of thinking that, okay, if I put any integer into a sum function, for instance, they're all probably going to be fine, right? Like, what's the difference between 1 plus 1 and 10 plus 20, or 1 plus 5 and 600 plus 25? Just picking random values. In that case, not really a big difference, right? Algorithmically, you know what the output will be. It'll be A plus B, and then you can check that. So that would basically be like the idea of putting it into a representative set. Now the issue starts to come into play where the edges of that set are, and we'll get to that with boundary value testing. But basically the idea with equivalence partitioning here is that, let me pop all these on so we can read the massive wall of text. Basically, you're going to divide your input data into representative sets. And what that means is that regardless of which value from this set, you should get an expected output from that. Now you can have multiple sets, right? You could have, like, say, negative numbers. You could have invalid entries. You could have valid entries. Whatever sets make sense that you can check to make sure that the output is correct there. So the idea with equivalence and why it's called equivalence, any value from that set is equivalent to another based on expected behavior. So what do we do here? We're basically just reducing the amount of test cases you have to run at the end of the day. So let's look at an example here. Got two text boxes. Say this is a web form or an Android form or something like that. You have to put your age and your phone number in. Okay, well, exhaustive testing, this would take forever to check, right? Every single possible value. An equivalence class here, let's look at age first and foremost. Let's say that we're only going to allow people ages 18 through 56. Completely arbitrary numbers, but that's our valid and invalid range. So one partition would be the set of valid numbers, right? 18 to 56 inclusive. What you would expect if I put any value from that range into this text box, you would get a representative output based on that input, right? 18 to 56 we're going to treat identically in code. Our test case should mimic that. And then depending on your perspective here, you might have one or two invalid sets, right? Maybe you want less than 18 and greater than 56, or greater than or equal to 57, depending on how you want to word it. But here basically we have three separate partitions of data, okay? And the idea, again, is that any value from any of these sets would be a test case that covers that whole range of numbers. You could take this and extend it to any data type that you want to put in there, right? Maybe it's enums, maybe it's a range, maybe it's an entire class. Maybe it's a JSON object or a packet or who knows what it is, but you can basically partition things into sets of data where you know that based on X input, you're going to get some form of Y output. And that is always going to be expected. Same idea here with mobile number down at the bottom. You don't really care what the numbers are as long as A, they are integers, and single digit integers, and B, that you have exactly 10 of them, right? So again, you don't care if it's 8675309 plus the area code or 111222333. They're all going to be fine as long as they meet the basic criteria. It will be treated as a phone number. Extend this to like an email address type or a username or password complexity or something of that nature, and you have similar kind of examples. But again, we're dividing data into sets, representative sets. Everything clear so far? Makes sense? Again, this could be any data type, it could be any function. You just have to basically partition things out-ish. Okay. So let me give you another example here. So let's say we have a factorial function, right? And we're still equivalence partitioning. Again, maybe one thing that would help is consider our test cases that we're writing, okay? So again, test cases have an ID, they have a description, they have the steps to recreate, and then you have inputs, expected outputs, actual outputs, right? So based on input data, you get output data. Clicked the wrong thing. Hey, that's fine, I'll take that. Okay, so input and output is what we're looking at here, right? What we're saying is with equivalence partitioning, we can reduce the amount of test cases we have to write to a much smaller group, a much smaller amount. So here's another example. Pretend that you're doing the CS101 thing of writing a factorial function, right? Probably deals with recursion, integers, standard stuff for, your first programming class, probably towards the end, because recursion's a tricky subject in and of itself. But we're testing a value coming in, right? So we only have one variable for input. So we have some value n. The expected output will be the factorial of n. And here we can apply an input condition, between 0 and 25 inclusive there, where anything below 0 or greater than 25 we're not going to accept for whatever reasons here, right? So here we can basically generate 3 equivalence classes. First one, n is less than 0, right? That is what our left side of our constraint. N is between 0 and 25. That is our valid value range, right? Any number in between 0 and 25 will have the factorial output of that. Again, obviously 4 factorial is different than 6 factorial, but algorithmically you can calculate out what that is, and you can check to make sure that's the right value. All right, what's 4 times 3 times 2 times 1? Well, you can, put any number in and just check it either manually or automatically. The other equivalence class, n is greater than 25. So we have class 1 outside of the range, lower, class 2 in the range, class 3 outside of the range. Any value from those sets are fundamentally equivalent from a testing perspective. And the key here is from that testing perspective, that we don't have to exercise this function with every single possible value, just with the ones that are going to make your code do that thing, right? And if I picked n equals 1 versus n equals 10, I'm still going to be able to see, does it give me the correct factorial or not? So ideally in that case, we should pretty easily be able to see. And you have to pick only one from the set, not necessarily, you can have multiple data points as long as you're demonstrating it's either working or failing. But again, idea here is to reduce the number of test cases you have to run. And we're going to talk about boundary analysis here, and then we'll kind of circle back a little bit. If equivalence partitioning makes sense, boundary value analysis should hopefully be a slight extension of that idea. And the one thing to consider is this is probably something you are already doing when you're writing code and you're doing little tests to make sure that things are working or not. Or whether you print out the current value of a variable, you maybe try it with a slightly different value and see, am I still getting a good value or not? Boundary value is, again, black box, where we're extending or complementing equivalence partitioning. So I've got a bunch of text to pop in here, but what's probably going to be easiest to look at is this particular figure. So consider equivalence partitioning where we made groups of input data, right? So this can be the exact same idea. So this is 0, this is 25, this is greater than 25, this is less than 0. So if this is like our factorial function. Boundary analysis, correctly spelled, boundary analysis. You're checking the edge cases, and then you're checking slightly inside and outside that edge case. Right, so if this is 0, maybe here this is 0.25 or 1, and this is like -1 or negative point something. And here this could be 25, this may be like 24 and 26 or something of that nature. Right, so the purpose with boundary testing is that, okay, you know that your data, and you can check the data inside the range, and it's probably going to be fine, assuming all your test cases are passing. It turns out most of the errors with our coding logic turns out to occur right around those edge cases. So like where you're doing your conditional checks. If x is greater than 0, did you check -1 or did you check -0.0001 or something like that? Those tend to be where the majority of the problems kind of crop up with at least black box testing and value checking, things of that nature. So you still have your equivalence classes, right? These are various aspects of our conditions, but the boundary testing adds a little bit more granularity to, okay, what's right, what's wrong here. And again, you're probably doing this already, honestly. So with equivalence, partitioning, and boundary value, does this make sense more or less? So with boundary, if we went back here to factorial, we'd have our equivalence classes, right? Doesn't change, but we might have a test case for each of these, right? So let's say n equals -5, n equals 10, n equals 30. This could be our 3 test case input values. Actually, let me pop up a thing here to help out a little bit with the mental picture, since I think waving my hands and doing this doesn't help too much. Console list, please. Thank you. So let's call this test case 1, partition 1, invalid. Input value, -5. TC2, partition 2, valid. Input value, 10. TC3, partition 3, invalid. Input value, 50. Okay. So again, these would match up with my equivalence classes. Now I have 3 test cases that I've written with expected outputs, right? So maybe expected out, oops, KK, using my vi keys. Expected output is, I don't know, false. We could say the same thing for 3. And then expected output is 10 factorial. I'm not going to go through and calculate that out. But here we have 3 test cases which exercise our function. Now, if we were going to add on boundary to it, so let's say this is equivalence, partitioning. Am I spelling that right? Equivalence or ants? I really hope I can spell it. No, this is E, equivalence. Okay, so here we have 3 test cases. Now let's add on boundary analysis. With boundary, am I going to cover this? TC4, let's say input value -1. TC5, input value 1. Again, our lower bound is 0. We could even check that value because based on our figure, I know I'm covering this up now. Let me do this. So when we tack on boundary value testing, just check the values right around that edge case. They might still all pass and then they might be superfluous, but you're getting a little bit more granularity with your testing. Right, and integers are easy. I mean, that's not necessarily something that you have to consider, but like what if they're floating point values? Or we have to check particular levels of decimals, or what if they're, again, say like classes with a whole bunch of attributes and a lot of moving parts, then this gets a little bit more useful, honestly. All right, but if that makes sense, question for you all then. What is the idea here about these in-between values? So we are partitioning our input set into a range effectively, right? And I'm saying you don't have to check them all anymore. But is this a problem? Do you have to worry about all of these in-between values like that 1 to 24 or -2 to -500 in our example? Are we going to get different responses if we happen to pick the right one? And do you have to worry about it? We should still check 1 or 2, right? I would say so, honestly. I mean, this is one of those things where it's tricky. Now, if the edge works, they all work. That's so this is kind of a trick question, I will say that. So this depends on how well you put together your partitions. It depends on how well you understand your code base and if there are any hidden gotchas, right? So to answer the Twitch chat here for a second, you should probably check multiples, right? Not just one. I mean, for your own mental sanity, right? Put together horribly and we don't understand the code at all. Right. And then you're doing test-driven development, writing your test cases along the way, and hopefully that clears things up. But the thing with this is that sometimes there are hidden edges, to use this example. Right? Maybe you're calling another dependency or you're referencing an interface or something that is bringing in a new factor that you haven't considered. That's why testing is never complete, it's never perfect. There's always going to be some little gotcha that you miss. So to me, I like to err on the side of caution and add in extra values, like said in the chat there. But ideally, it catches everything. But in practice, that's not always true. So you have to understand the code very, very well for this kind of thing. But those are two examples of black box testing. And again, it's input and output driven. Pretty straightforward, honestly. Based on what we just talked about, you should have a pretty good feel that the unit tests, integration tests, system tests I'm asking you to do for your term projects, these are all pretty much black box tests, right? You're not checking paths of execution, you're not checking coverage, you're just checking behavior. And again, behavior is what the expected outputs are doing. That's the easy stuff. It gets a little bit trickier with white box testing. So this is where you know what is happening inside of the code base. You can see the algorithms, you can see the conditional statements, branches, loops, all of that fun stuff. White box testing, to me, is a lot more involved. Now, with white box, we have some different metrics here to cover. Black box, you just care if it passes or fails, right? Just matches the expected output. Good, we're done. White box, there's a little bit more to it. So we have some different types of testing techniques that you're going to talk about. We're going to mainly go into basis path testing in a little bit, but just be aware that this tends to be a little bit more difficult. So, at least to me, a little bit more difficult. First, let's talk about coverage. So coverage is checking to make sure are things covered. Basically, did you execute that particular line of code? All right, and what I mean by this, to kind of set the stage before we go into the different categories, coverage is making sure that some statement of code, right, some line of code that you've written, that it actually gets executed at runtime. Consider, like, an example would be if you have an if statement that never triggers, that code is basically dead code, right? Because you can never get into this if statement. It's more than likely unintentionally that you never get there, but it's dead code and it should be taken out because it basically demonstrates some weird black hole state that your system can get stuck in, possibly. So with this, we have some different metrics we can talk about here. So the first one we can look at is line coverage. So basically, is every single line of code executed at least one time? And the thing to keep in mind with this, these different types of testing here, you are writing test cases. Again, same thing, test case, steps, inputs, outputs, all that fun stuff. But you're writing the test cases to make sure that lines of code are being executed. So for that example that I just said with the if statement, you would have a test case that says input conditions to the function are X, Y, and Z. Based on that, this if statement gets triggered. And then you go into that block and run the code. All right, so with line coverage, basically you are creating a suite of test cases that makes every single line of code run at least one time. Okay, so you don't have any dead code basically. Can be very, very tricky to do with large code bases. Consider it almost similar to exhaustive testing where you're checking every single possible instance. But this is something that's a little bit easier. It's honestly half the time something that can be done automatically by your compiler or by your static analysis tools. Is it possible to get to this line or not? All right, so that's line coverage. Everything is run once. Branch coverage, every single branch statement you have, whether it's an if statement, whether it is a loop control structure or a switch or something like that, anytime you have branching code, as long as you are able to get into that branch, it is happy. All right, so 100% branch coverage. If I have a whole bunch of if statements, every single possible branch is entered, or every single loop is entered, or something of that nature. If I had, say, 50% branch coverage, only half of my lines of code are executed. Again, this is driven by the test cases that you're writing. It's not that the program knows how to do it, it's that you are forcing the program into that state to run that code. Right, so that's branch coverage. Go down every path. Conditional coverage, basically you're checking, these decision statements and making sure, have you checked every possible state of that condition? Right, so if you have like if x equals 5, or sorry, x equals 5, you would check for, you'd replace x with 5, you would replace x with 6. You have both sides of that condition being executed, right? The true side and the false side. So basically, you're checking each outcome. We can merge these two together as well. So these are not necessarily the same thing, right? We can have branches that get executed without every single condition being covered, right? So it's possible to have complicated if statements where, yes, we got into every single possible if, else, but we didn't check every single conditional in that statement. It's kind of a fine distinction, but if you sit down and look at like an if statement, it should make sense. You're checking which blocks of code you're entering, and you're checking the actual conditionals separately. Branch/condition, you're merging the two. We can go a little bit further with that too. We might have multiple conditions, right? So it's not just if x equals 5. Maybe it's if x equals 5 and y is greater than 10 and z is less than 0.5. Basically, you have multiple conditionals strung together. Multiple condition coverage, make sure that every single one of those conditionals is checked, basically. And then you can link that up with branch coverage, make sure every branch is run, and so on and so forth. But again, we're getting to that check paths of execution. And the last one here we're going to talk about is actually going to take us into kind of the harder way of testing things where we actually have to deal with mathematical formula, is path coverage. So here, and again, there's minor distinctions between all of these, but basically you're just checking, is X line of code run? Here you are checking to see, are all the different possible paths of execution run at least one time? And there, it sounds very similar to everything I've already been saying, but basically if you were to graph out your program, which is what we're going to do here in a moment, you're going to start seeing, if I have this set of values, I can go this way through the program. If I pass it different parameters, I go this way through the program, and then maybe I come back at the end or something. Basically, path coverage is, have you checked every single possible path of execution for this thing you are looking at? Again, branch and conditional coverage is only really concerned with those branching statements. Path coverage is the whole thing. And the thing will depend if you're looking at functions or classes or programs. Your perspective can change based on what you want to see, I suppose. But basically, we have these different ideas of coverage. Generally, if you're going to be checking coverage, you're looking for a very high percentage, ideally like 100%, where I have checked, yes, all my code is executed. Okay, here's where it gets a little bit interesting, so please stop me if you're looking for questions. Is this automated at all? It can be automated, yes. So I would actually, yeah, it can be very tricky with large programs, absolutely. In Java, there is Jacoco. In Python, there is coverage.py. There are tools in C. I don't remember what they're called. Actually, if you let me pop this open here. Um, hmm, crap. Travis, and it was a Medium article. Anyway, Jacoco. So there is basically a hook for Jacoco in that Travis CI Medium article that I linked. But basically, you can plug in this tool, which tells you what is your coverage of your program. So then basically you get a list of how many lines of code never get executed based on your inputs. So yeah, automation definitely possible. There's also coverage.py, yeah. I haven't gotten this one up and running yet with my local installation, but basically you pass it a Python module. It tells you, here's your coverage value based on what you want to look at. So there's a whole lot of things you can do with that. I agree. Automated tools are very, very necessary for this kind of a thing, though. All right, so with basis path testing, this is where it starts getting a little bit more involved from your perspective. This is basically a way to figure out how many tests you need to write based on how complicated your program is. And what you're going to be doing here is you're going to be calculating something called cyclomatic complexity, which I've got here in bold. Basically, this just tells you how many paths of execution you have in your code base. And how do you figure that out? There are a handful of formula you can use. Basically, they should ideally result in the same number. But first thing you're going to do is draw a flow graph of your program. And this could be an automated drawing too, by the way. This can all be automated, but I'm going to show you how to do it manually. Basically, you draw the full flow graph, which basically shows you how to get from statement to statement, and if there are any loops or conditionals or anything like that. And then you figure out how complicated it is, and then you figure out how many test cases you need for that. So here's a pretty straightforward way of drawing a flow graph. So if you've ever heard of a control flow graph or anything of that nature, this is basically what you're seeing here, where basically you focus on some unit, whether it is a system level, here you have a function level path, but every actual line of code gets an ID. Could be your line number, for instance. We don't really care about the variable creation lines. They don't really do anything for us. But once you start getting to assigning and actually doing stuff, we start counting it. So here we have a graph. If you've never heard of a graph before, it's basically a tree, except we don't have the notion of what the top is. It can be directed any way you want. Each bubble is called a node. Each line is called an edge. Edges generally will have direction, so you see arrows. Basically, one goes to two, two goes to three, blah, 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 blah. Makes sense, hopefully. Here we have a very, very simple function that we're just summing up until basically I is going to be greater than n in this case. So let's pass in some value n, initialize I to 1, or sum to 0. While I is going to be less than or equal to that value n, update our sum. So we're going to start 0 plus 1 equals 1, increment I, 1 plus 2 is going to be 3. Is that bigger than n? Keep going until we get a, appropriate sum value here. Doesn't matter, but from our perspective, we're using it to illustrate this flow graph. So line 1, right? This is I equals 0. 2, sum equals 0. 3, while I is less than or equal to n. Here we have a branch. And what we can see here is that we have a true or false, right? Loops are basically true or false. If it's true, do the loop. If it's false, you're not doing the loop. So if it's true, execute line 4, execute line 5, go back to your conditional, right? So you have that loop construct. Once this is no longer valid, you go to return sum, right? Which is 6. So this is a pretty simple flow graph of your program. Now you can hopefully see here, and again, this is related to complexity and how many test cases we need to write. We have two paths of execution here, right? So we have 1, 2, 3, 4, 5, 3, 4, 5, 3, 4, 5, 3, 4, 5, 3 to 6. Right? We don't necessarily care how many times this loop runs. We just know we have this path here, right? So that's one path. Other path, 1, 2, 3, 6. In the case for that would be that we never enter this loop. So we have two distinct paths of execution here. And again, simple example would be much more complicated for a real program. What that means is that we need to write test cases to get this program to run those two different paths of execution. And then from a coverage, um, path testing perspective, we're happy because we've exercised the code base. What are our test cases? Well, to get into this loop, we just have to have n is greater than or equal to I. Right, so we could say 2 is greater than 1, right? So then we go through that loop. What's the case where we go down the false path? Well, I has to be greater than n. We see that I starts at 1, so that means n has to be less than 1, which means 0 or less, right? So then now we have two cases where the input values are different and we're going down different paths of execution. There's probably a lot more to it, right? We have other values to check and all that for a more real program, but here we are at least checking paths of execution. Again, keep in mind, this is white box testing, so we know all of this stuff because we're basically at the developer level, right? So, maybe we will save this for next time since we're going to be getting into that. Basically, visually, you can see the complexity of this program would be 2, because we have two paths of execution, right? We have 3 different formulas which we can use to basically calculate that out. So how many edges, how many nodes do you have, how many loops do you have? That all would kind of factor into some of these different questions. But I think that would be kind of like a 10-minute discussion of talking about these formula. So what we can do is end a couple minutes early and not leave you waiting for more, I suppose. Any questions from today at all? Any questions regarding the final or anything like that? I have started grading your homework too, so those should be coming in pretty soon. Just homework 5 is taking way longer to grade than I thought it would. I asked for too much, I suppose. But, all right. If there are no questions, I will end the stream now and I will see you all Wednesday, all right? I have a couple of questions about integration testing. Hey, if you want to shoot it to the general chat, that's fine. Otherwise, we can do it separately. Since we have a couple minutes left. But there are more. Okay, that's fine. All right. Well, let me address that one really quickly, and then you can message me separately if you want. So I've had this question a couple times. That's why I want to talk about it. So unit testing, I think, makes sense more or less to everybody. It's one tiny unit that you're checking. Integration testing, you're bringing modules together. System testing will be the system as a whole. So if I'm using, somebody's Unity project, for example, unit test would be one function. Integration test, let's say, bring together the movement system and the graphics system, or, the NPCs and the AI and the player or something of that nature. System testing would be your entire game as a whole. And if you're struggling with figuring out what tests might apply better to system testing, you might want to look at your non-functional requirements because those tend to be more system level focused. And a lot of your requirements that are functional are probably very targeted. Non-functionals tend to be a lot higher in scope. But yeah, if you want to drop me a message on Discord or through email, feel free to do that. Otherwise, I will see you all on Wednesday. So hope you all have a great day. All right. Yep, anytime. Thanks for participating. Bye, everybody.